Okay, so this is the higher tier question 3. I've had to do this in a slightly different way because I'm going to use my original mark scheme rather than writing it out for you, because getting hold of one of these papers was very difficult. So carbon 12 and carbon 14 are isotopes. So we can identify this from the fact that they've both got an atomic number of 6, and that tells us they've both got 6 protons in their nucleus, but carbon 12 has a mass of 12, which means 6 protons and 6 neutrons, and carbon 14 has a mass of 14, which means it's still got 6 protons, but now it's got 8 neutrons. Okay, so the question says, explain in terms of the number of particles why carbon 14 has an unstable nucleus and carbon 12 has a stable nucleus. And what they could have used here, instead of the word particles, they could have used the word nucleons, which is a word that sometimes crops up, and it means particles in the nucleus. Okay, so if we have a look at our knowledge organizer for the WJC, and if we have a look over here, we can see that of the 2 isotopes of carbon shown above, only carbon 12 is stable. Carbon 14 is unstable because of an imbalance between the number of protons and neutrons in its nucleus. So that's the sort of thing they were looking for in your answer. So what I wrote originally was the ratio of neutrons to protons is 8 to 6, which tends to produce beta decay, and we could add to that this is an imbalance. So they're not the same. Okay, imbalance in nucleons. Okay, so there's 3 marks here, so we do need to perhaps mention the ratio. We need to mention that that is imbalanced, and we need to possibly mention that that produces beta decay. Okay, so those are the 3 marks for that question there, or part of the question. Okay, the next question says an unstable nucleus becomes more stable following the emission of radiation. Complete the table below. Okay, so we were looking at the type of radiation, the symbol, and the description. So again, if we just briefly look back at our knowledge organizer, there is a table here which describes what we're after. This is been rotated through 90 degrees effectively, but we've got the alpha particle, the beta particle, and the gamma radiation. So if we refer back to our question, we'll find that the first one is the gamma, and we're looking there for the symbol for the gamma ray. So let's just double check we've got that right. So here we're using a Y, which is a bit of a cop out, I'll be honest, but no doubt you can get away with that. And then that was all you were asked for the gamma radiation. Moving down, we've got the alpha particle rather, and you were asked to describe the alpha particle. So I've written here a helium nucleus, and if we briefly look at the knowledge organizer, then we find that it's described as a helium nucleus, but in more detail, 2 protons and 2 neutrons. Now, whether or not you'd need to put that down, I'm not sure, but it wouldn't hurt to do so. So we've got to put that down. So that's 2 protons and 2 neutrons. That's just a belt and braces approach there to make sure we get that right. And then the final question, part of this question rather, is asking for some information on a beta particle. Okay, so you can see there that I've put the beta particle as no mass, it's got a charge of -1, and it uses the beta symbol, and I've described it as a free electron. So I'll just double check that against the knowledge organizer, and in the knowledge organizer it's described as a high energy electron. Okay, so again, we'll add that to the answer just to make sure, absolutely sure. And you'll notice that here you've got a couple of alternatives for the symbol. You could simply use the E, that stands for electron, or I prefer to use the beta symbol because it does make it clear that this is a beta particle that's been emitted from the nucleus and is not simply an ordinary electron that's got a bit lost. Okay, so if we go back here, so we'll put in here the additional information, high energy. Okay, so that was number 3.